Cool. Okay, so our speaker this morning is Eric Vautier. I hope I'm pronouncing that correctly. He is did his university studies and PhD at the University Claude Bernard of Lyon and got a staff position at CNRS in 1990. At the time, it was called the Institut des Sciences Nucléaires and now Laboratoire de Physique Atomique at de Cosmologie de Grenoble. In 2015, he joined the Institut de Physique Nucléaire d'Orsay and is now Laboratoire de Physique des Deux Infinités Irene Juliette Curie. I am going to apologize now for my pronunciation there. His main background is experimental physics and performed experiments at NICEF, Saturn, ELSA, MAMI, CEBAF, and recently ELF. Is now at JLab since the early 90s and developing along the years a specific expertise in polarization phenomena, observables, polarimetry, and associated detector techniques. His main contributions are to nuclear structure measurements in elastic and E'(P) experiments and nucleon structure measurements with DVCS. After the first DVCS experiment on the neutron Hall A, his interest in that has led to investigate positron beams and the physics of positron beams. This research began in 2007 together with Joe Grims at JLab. Hello? Oh. This led to the PEPO experiment, demonstrating a new technique for producing polarized positron beams, which is now the basis for the positron injector of CEBAF plus. Most of his scientific activity is now dedicated to positrons at JLab with the CEBAF plus working group and the Jefferson Lab positron working group. Thank you for being here with us today, and the floor is yours.
Okay, so first of all, thank you for the invitation and the possibility to show what we have been doing. So that should be okay. Yeah.
Yes, we can see that.
You can see that. I should do that. Okay. Then this and here I have something. Oh, sorry, you would like. Come on. Yeah. Yes. Okay. You see the pointer and everything?
Yes, we do.
Okay. So yes. So as you said in introduction, this work has been starting since several years, and it's not only 2017, but yeah, we indeed started with Joe in 2007, and even people before us were already thinking about positron beam at Jefferson Lab. So I will present a work which was done from with a lot of contribution, and some of the people of in the audience have been contributing to that. So in any good movie, you always have the main character, the star of the movie, and he is leading the effort. So I would like to introduce you the star of that story, Mr. Positron. So that guy was appearing first in 1928 in an equation. The first equation talking about relativistic quantum theory and for spin 1/2 particles. So appearing as a very strange thing of a particle with negative energy, but okay, that was just a theoretical concept, so why not? But 4 years later, and in fact, this experiment was just happening by accident because Carl Anderson at that time was looking at X-rays, And he found that this is a picture of one of the other observations. So this is a plate which is in a magnetic field. And so they observed a curvature which was corresponding to positive particles, but which was, at that time, it was the proton was the only one known, but it was not the neutron. And in fact, this was the first discovery of the positrons, and this was the very first experimental evidence of antimatter. So all this group of people working working on positron beam at Jefferson Lab and positron physics at Jefferson Lab, we are all grouped into the Jefferson Lab positron working group, which is essentially a group of people of about 250 physicists. And we recently published a white paper which contained ideas of experiments more or less developed. Some are really going to really almost an experimental proposal. Some are just conceptual ideas, and you have a very large scale of physics, and this is what I'm going to try to talk a little bit about. So when you have a process which results from, in fact, you do, as long as the electromagnetic interaction is concerned, you don't really have any difference between electrons and positrons. It's just exchange of virtual photon. But as soon as you have a process which is a combination of two QED-based amplitude, you have interference, you have additional contribution, and the difference between electrons and positrons can help you to reveal the interference between these two amplitudes. And this concerns the case of the two-photon physics and also the case of the generalized parton distribution. If you have enough energy and you can access also electroweak physics, you can also, I went a little bit, no, that's okay. Electroweak physics, then you may use the electronic probe to test the structure of the nucleons. So that's in experiment of deep inelastic scattering, where you are going to probe the strand content of the nucleon, or you can also do some specific measurement on charge production. And this is what a class of experiment of which I would say charge current physics. And then if you do have a very intense beam, polarization, good quality, then you can really try to test prediction of the standard model by comparing electrons, response of electrons and positrons to of the system, or by studying a very specific mechanism. And for instance, you can try to search for a light dark matter with positrons, investigate charge conjugation violation, or try to study some lepton flavor violation. And one thing which is maybe a little bit far from our physics, but not that far of the physics, is also the slow positron application. This is something which is developed in US and also in other countries like Germany or Japan, and where you are going to use positrons to probe materials. And you can, this is techniques which are called positron annihilation spectroscopy, where you annihilate with the atomic electrons and you measure, you are really measuring default inside the materials. This is very good range of application, which can also be used in spintronics, and you can also think about antimatter production and energy productions. So this takes the news for this year with respect to the Jefferson Lab positron program was the approval of 5 experiments. essentially dealing with generalized parton distribution and two-photon exchange, and approved in a C1 condition. C1 means that obviously the positron beam need to exist for the experiment to happen. So this is essentially what I will be talking to you today. So you have the outline of our presentation, the first part on the two-photon exchange, the other one was the generalized parton distribution, and a few other examples before giving you some information about the beam itself and the accelerator project. So let's go to the two-photon exchange. So it is, so since the measurement of the polarization transfer in all A, which measures the ratio of the electric to magnetic form factor of the protons and giving this decrease. So since these very first measurements, the question was asked whether the one-photon exchange approximation for the electromagnetic interaction was enough to describe the interaction. And this is coming from the disagreement between this polarization measurement and the measurement, the previous measurement, which were obtained from Rosenbluth separations. So if the two-photon exchange, two-photon exchange contribution exists, then the form factor, the electromagnetic form factor of the nucleon is no longer described by 2 quantities, but 8 quantities, which means that you need to have enough observables to do these measurements. But this is an hypothesis, and this was not yet experimentally proved or denied. And here, Jefferson Lab equipped with a positron beam have a unique opportunity to really bring a definitive answer to this phenomenon. So are we expecting to do that? So first of all, we can investigate the measurement and compare of the cross-section. We can and compare the cross-section of positrons with respect to the electrons, which is essentially giving you access to this term, which is connected to the two-photon exchange, and which appear here in this formula of the reduced cross-section as this term where the sign is changing here. So if you do this measurement, you can access that information, and in principle, if try to tell whether there is or not two-photon exchange. Another way of doing that, and it could be to do a super Rosenbluth separation. So that's a Rosenbluth separation, but using the scattered proton instead of the electrons. And the principle is shown here. So if you do measurement at different epsilon, different virtual polarization of the virtual photon, you can have the slope, and you have the slope of the electron beam. So this is the one of this reduced cross-section as a for different epsilon measurement. If you do measurement with positrons, you would obtain a different slope, which is just the opposite. So comparing the two, you have twice the two-photon exchange. So you are improving by comparing the slope of the Rosenbluth separation. You are improving your sensitivity to the two-photon exchange. But not only, if you then do the average, you are going to obtain a certain slope that you can compare to the slope you would obtain from which you can infer from the polarization measurement. If you do have a difference there, this means that there are something else than the two-photon exchange contributing to the difference of the between polarization and Rosenbluth experiment. The third thing that needs also to be investigated is the polarization transfer. The calculation of the two-photon exchange, which were predicting the effect on the cross-section, are also predicting a very small effect on the polarization transfer. So this needs to be really assessed experimentally in order to make sure this is there. So, of course, these people have been studying and doing experiments trying to investigate that since 20 years that this problem appeared. And these are this is essentially an experiment at CLASS, at Web3, at Olympus, which we are trying to measure two-photon exchange. And you have on that on this plot the Q-square epsilon range which was investigated, and the size of these circles is corresponding to the statistical to the error bar. And you do have here the best experiment in terms of statistical quality, which is the Olympus experiment. And if you look at the result of the Olympus experiment, which are here on that plot, on the right plot, compared to different prediction, you seem to see that, okay, maybe there is something, but the effect is quite small. And this is one of the, this was one of the very, very big difficulty of this experiment. It seems to be consistent with something, but it's not really convincing. So the problem is really to measure the effect and to measure the effect in a region where the effect is large. And this is one proposal which has been submitted. It's one of the 5 which was approved this year, which would be to measure elastic scattering with electron and positrons using the class detector, and really to map out in the Q-square epsilon range the two-photon exchange. So you have here the range, kinematical range, which is expected to be covered with different beam energies. And also what is important is you see the ratio, and you see that Olympus was in that range, a few percent, 1 to 2%. But here, by increasing the Q-square, we can access a region where the effects are close to 20 or even 25%. So this in that sense, this experiment should find something. If there is something, it should find it and it should show it. And so of course, two-photon exchange are not only connected to elastic scattering. You can also ask further question with respect to scattering of electrons, which is multi-photon effect, like the dispersive effect in E prime inclusive scattering. And you can also ask yourself whether or not there are two-photon exchange in the deep inelastic scattering. And there is one experiment which has been approved too also, and which concerns the measurement of Coulomb correction in the DIS regime. So it's essentially symbolized on this plot where people want to measure deep inelastic scattering on gold and deuterium, and they want to measure that on positrons and electrons. So they are going to make a super ratio of, which is very nice because you can do measurement of electrons, and later you do the measurement of positrons, and you don't have systematics because most of that is going away in the super ratio. And this is showing here we should expect one if you don't have any Coulomb effect, and this is the way you may expect if you use a Coulomb correction that people are typically using, but which are based on extrapolation of elastic scattering. And of course, this is not an exhaustive list. There is also other ideas which were developed in the positron white paper. I want to go now a little bit on the generalized parton distribution side. So generalized parton distribution are essentially a very nice and parametrization of the structure of hadrons. And because they do contain information of the correlation between the partons, they have also not only it's not a static picture that you can obtain, but it's also a dynamical picture. So you can obtain information about the dynamic of the system, that's the angular momentum, or the distribution of forces of the nucleon. Of course, to get some insight into the nucleon structure, you have an object which is a little bit more complex than the form factor, which is depending of 4 main quantities: Q squared, which is the art scale here, X, which is the average momentum, average parton momentum, the skewness, and also the momentum transfer T to the nucleon. So what kind of information, what kind of physics information can we get, for instance? So that's this is concerned, for example, the transverse profile of the parton inside the nucleons as a function of the momentum carried by the partons. In order to get that information, you see that this information is obtained from an integral, and you need to have a very good knowledge of these GPDs over the physics space. Another source of information, which is an access to the orbital momentum carried by the parton inside the nucleon, and which is also, so this is a G-sum rule, and which is also involving an integral over a large phase space. So you need the information about these 2 GPDs. And another information, which another class of information, which is the second moment, the median moment of the GPD H, and the X dependency, the Xi dependency. So the Xi dependency here, which is in this D1 of this D term, is very important to determine the dynamical information, so the distribution of forces inside the nucleon force and strands. And in this business, the positrons are bringing one specific information. So if you combine unpolarized positrons and electron beam, you would access, you have a direct access to the real part of the Compton form factors. And if you would combine polarized and unpolarized positron beams, then you can access the imaginary part and also try to probe higher twist effect. I would say that you can also access the imaginary part only by using polarized electrons, but this is not going to be a completely pure signal. I'm going to explain what I mean by pure, and this is essentially here on this plot where you on this slide, sorry, where you have the expression of the cross section. E means the electron beam charge, and P is the polarization of the beam. So you have 2 amplitudes, they interfere, so they give you rays to 5 different amplitudes. 2 of them are depending on the beam polarization. The interference contribution is depending on the beam charge. So you can you clearly see that if you combine electrons and positrons, you can isolate these 2 contributions. And if you have the polarization on top of that, you separate these 2. And you can also do the same things, assuming, of course, that you know the Bethe-Eichler process, which is in principle, which is true because this is the essentially radiative correction to elastic scattering at small t. So small momentum transfer where we don't have that issue of 2-photon exchange. And you have exactly the same phenomena with polarized target, because you need to do measurement with polarized beam and also using a polarized target in order to access different combination of the Compton form factors. So in that sense, polarized electrons and polarized positrons allow you to separate in a very it's not ambiguous, it's not model dependent. This is just you play with your experimental tool and you separate all the amplitude to the cross-section. And this is the best gift that you can give to your fellow theorist friend in order to do the interpretation after. So, of course, it's a little, this is simple, but it's a little bit more complicated. You don't access directly the GPD. What you are measuring is the Compton form factor. So it's essentially the same thing like the elastic form factor, but more. This is the same, I mean, physics quantity, but this is a GPD. So this Compton form factor, so the cross section is proportional to an integral, and which gives you real part and imaginary part. And depending on which amplitude you are going to measure, you will access different combination of the 4 GPDs, which goes into the description of the proton structure. And so if you have the DVCS amplitude, here you can see this, square of H tilde, E tilde. So this is a very, very difficult combination of the Compton form factors. But if you are able to do the interference contribution to isolate that, you see that you have a much easier expression, at least in order to interpret where you have also the form factors. So the interest in really separating this amplitude is to have the ability to access differently this and uniquely these contributions. Here also, there was previous measurement, and those measurements were essentially coming from ERA and Hermes, where they really demonstrate at that time the existence of the BCs, of the beam charge asymmetry signal. And you do have also measurements coming from COMPASS using polarized muon beams. But it's everything is here. Everything here, all the results which are existing is here. So that's quite it's quite insufficient in order to really have just the ability to, let's say, try to do the transverse profile of the partons inside the nucleons. So one experiment is going is the one which was also accepted this time is going to do beam charge asymmetries using polarized beam. And this is going to give us, so you have the expressions here which are going to be measured. And this is going to, so the unpolarized charge asymmetry is giving us a direct access to the Compton, to the real part of the Compton form factor. So if we are using polarized beams, then we will have the imaginary part. And if we are averaging of the beam charge, then we have a signal which is really sensitive to higher twist effect. So what do I mean here by sensitive? It is just that this signal, if there is no higher twist, the signal should be completely zero. So that's really a very, very good signature, sorry, of this higher twist effect. And you have here on this plot, you have here the different, some different kinematics showing. Let's take the, for instance, the red one. So you have the experimental projection of unpolarized charge asymmetry and different model predictions. And of course, as soon as so you are moving from small x and small q square to large x and large q square. And of course, large x, large q square, the statistics is becoming small. Another experiment is going to measure the cross-section with positron beam, very precise measurement of the cross-section with the neutral particle spectrometer. This is in all C, using the HMS spectrometer also. So this experiment is currently running with electron beam. They are currently taking data. And they are proposing to do similar measurement with the positron beam, where you have here red and the overlap between the kinematics they want to measure, and they would be able to do exactly the same kind of separation. Another interest, it's still at the level of letter of intent, and was developed also in the positron white paper, is to measure the DVCS on the neutron. So the neutron has this very nice feature that the F1, the Dirac form factor is zero. So if you look at the combination of the GPDs, you get sensitive. You are very sensitive to the eGPD. And the eGPD has this very nice feature that this is the one which flips the spin of the nucleon. And so this is a piece of information which is completely new and which cannot be accessed in deep inelastic scattering, for instance. So, and this is, of course, quite important in order to do the G-sum rule. You can measure H on the proton and try to have also E from the proton, but from the proton you need a polarized, transversely polarized target. So you have here the expression of the unpolarized charge asymmetry, where you see the sensitivity to the EGPD and some sensitivity to H tilde, which is also kinematic dependent. But the benefit of the positron beam here is expressed here on this plot, where so this essentially red points correspond to electron beam only, and blue points correspond to positrons and electron beam. So here it is assumed that you do the measurement on with an electron, or you do the measurement with the positrons, and you try to extract the Compton form factor E from that. And you see, and of course, since okay, you have the extraction method is concerned, but the idea is here to show that if you just have only electron, you can only extract information in very specific kinematics, while if you have both electrons and positrons, you would be able to take advantage of the full kinematic coverage of the class spectrometer. Tell me if I am too slow, and I have tendency to take a bit of time, a bit too much time. So don't hesitate to warn me. Another things, and which is also an experiment which is going to start soon with electron beam, is to measure DVCS on a nucleus. So here you are going to study the partonic structure of the nucleus, and a case nucleus here is helium-4, because helium-4 has this very nice feature of spin 0. So you have only 2 GPDs at leading twists. And this is, there was a measurement at the, from class 6, which was showing that the experiment was possible. And now a completely new recoil detector, ALERT, was designed and is going to be in operation soon next year. And so here the idea is to measure either to study the DVCS on helium-4 to see here you have this observable, so you are going to obtain information about the GPD of the nucleus, or to have, you can also do measurement on helium-3, and helium-3 is having a very strong sensitivity to the neutron GPDs. So this is a way also to access the neutron GPDs. Going one step further to deeply virtual Compton scattering, so we go to double deeply virtual Compton scattering. So why double? Because the photon which was real in the final state of the DVCS is becoming virtual in that case. And here we are saying, so this virtual photon decay, and typically you would like it to decay in a muon pair, because if it is of course it can decay in an electron pair, but then you don't know which is which if you do that. So the double DVCS is a very nice process. Why? Because when we do DVCS experiment, either with electron and positron beam, we are limited to evolve along a given kinematic range. If you compare the two information, so this information which is here and here. So you are the Xi prime and Xi, we are measuring that through this imaginary part. You are measuring that in the DVCS in that region. In time-lapse Compton scattering, which is just the same process, but you have an initial. This is going a time reversal, so you have a read photon in the initial state. you are also limited to access this region. So you don't have any information in that region. So you cannot access by independently, or you cannot access at a given psi, you cannot access the GPD at a psi prime, at a different psi prime. So in order to do that, you need to have an additional virtuality, which gave you an additional lever arm, and you can you would have then two scaling variables to describe your process, psi and psi prime, which are expressed as a function of the quantity that you can measure. A nice feature here is when you have q prime square, which goes to q squared. You see that psi prime is essentially changing sign, and this should goes to also the change of sign is H and E GPD, and this is a very nice signature of the GPD's universality. So the process is not only a little bit more complicated, but also is very the cross section is much smaller since you have one additional photon in the final state. If you do so, but you have exactly the same kind of structure where you do have two beta-Hitler process which contribute to the cross section. They are interfering between the two, and you have also the DVCS and also interference contribution. If you would do an integration over the muon pair, then you have a very similar structure with respect to DVCS. And you can see that once again, that if you play with the lepton beam charge, you can isolate these two contributions. And if you play with the polarization, you can single out these two. There was a letter of intent which was proposed this year, but to do the measurement with the solid detector, and the solid detector complemented with a muon detector here. And you have here, so the experiment was proposed to operate with electrons, but it can be extended also to operate with positrons. And you have here the beam spin asymmetry. So and you can see here the change of sign I was mentioning before, depending on the kinematics. And here what we could obtain also with the beam charge asymmetry and with also the change of sign. So that, and this, we were essentially proposing to run over the 50 days in parasitic mode, which are already approved, so JPSI experiment. And so adding 50 more days with positron beam would provide these two things. Another example is an experiment also, which is trying to investigate the axial neutral current, and which is in fact which appear in this Lagrangian, and this quantity was measured only at once with muon beams at CERN, and this is this results that you do have here. In this proposal, they show that comparing unpolarized cross-section on deuterium, so you compare electrons and positrons cross-section on deuterium, you can access that quantity, and which is here this quantity which is expressed in these coefficients, and this is giving you this was put into the solid detector, and this is the projected results. But the same quantity can also interpreted to help you to access this F3 structure function, and you see that the results here, they are also very promising. Of course, this is a very demanding experiment, very challenging on experimental point of view. You need to master all systematics in a at a very high level. So it's not going to be a first generation experiment. Another way, another experiment, which is still at the level of letter of intent, is to study the direct annihilation of positron and electrons, which to provide a light dark matter. So, and you would have a detector where you send the positron beam, and you have the interaction. So the detector is also active, and you are measuring all the energy, which is you are measuring all the energy. So if you have something is missing, you may interpret it that as the light, some energy going into a light dark matter particle, and which with that expression. In order to do that, you need a very you need some nice beam structure, but that's something which can be achieved. And the nice feature of this direct measurement is that you are you have the projection here, and you can see that you are you are becoming to be sorry, you can reject some scenarios, which is very interesting. A few words about the beam. So the beam, how are we going to do the polarization? So the polarization is something that we have been testing first at the PEPO experiment, and the polarization of the positrons is going to obtain from the polarization of an initial electron beam. So everything is happening in the same target. You have Bremsstrahlung and percuation, and all along these two processes, the polarization is transferring from one to each other. And this is what was measured at low energy here, and you can see that we can obtain the polarization which are very close to the electron beam polarization. So a polarization transfer which could be very high, and which is also decreasing when the beam energy is increasing. But this is the basis that we are going to use in order to produce the positron beam. A new positron injector has been designed. This is the thesis work of Sami Abed, which was defended just 1 week ago. And so you are going to send this electron beam on a tungsten target. You do have a collection system there, which is made about solenoid and cavities. And a first chicane where you are going to select the momentum of the positrons. Then you accelerate the positrons, and another chicane where you are going to manipulate the bunch length, because you need to have that. This beam is not going to CEBAF, and CEBAF is accepting beams with specific bunch length and momentum spread. So the nominal quantities which are considered for the experiment is that if you want to use a polarized positron beam, what we are looking to is to obtain beam intensity larger than 50 nanoamps with a polarization of 60%. And in the case the polarization is no longer a concern, we are targeting at least a current of 1 microamp. This new injector is going to be installed in the LERF. So the LERF is the low energy recirculator facility. And so it was hosting years ago the free electron laser at Jefferson Lab. It's not essentially empty except that part. So we would use, but the very nice feature is that the building is equipped with all the capabilities in terms of electricity, shielding, cryogenics, and so on. So this head is still existing, and everything else have to be put. So you are producing the electrons here, accelerating them to 120 MeV, having this new injector of positrons. Here you have a spin rotator, so you may want to manipulate the spin before going into the CEBAF, and then the beam is going to CEBAF. If you put that on a large map, so we are essentially here. So you need a bit of civil construction here in order to connect to the existing tunnel. And then you have a complete, this will be only a transport line. So you transport the beam, you don't do any acceleration, and it would be hanging on the ceiling. And you are going all around and go to this injection point where you need to have particles with 123 MeV. So this is the group of people which is working, and you have on the accelerator part, and you do have here a very strong and active R&D developing. So to summarize, there is really a rich and high impact experimental program which is asking for intense CW, polarized and unpolarized positron beam at Jefferson Lab. This will help us, this will enable to measure new observables and to explore a new reaction channel. And this technology that we are trying to develop, it would be a real world premiere. There is a strong R&D effort and towards the final design and implementation of polarized and unpolarized positron beam. So experimental capabilities that if you are interested to do an experiment and want to propose, or even if you are interested to contribute to the positron working group and develop new ideas. So it's not only the C, what we are calling C plus BAF at high energy, so this going through the accelerator, but you have also to consider that before going into the accelerator, particles are produced at the LERF facility, and you will have here very interesting beam for some experiment. You will have at low energy, you do have an electron beam which will be at least 1 milliamp with very high polarization, which could, let's say, something which is similar to the MESA, or not similar, it's a super MESA in terms of the polarization. MESA being a facility which is planned under construction at Mainz in Germany. And you do have, you would have, of course, the same performance for the positron beam, and the energy will be that has to be considered is 120 MeV at most. And with this, I am finishing, and thank you for your attention. And well, I'm happy to take your question.
Thank you. That was very interesting. Let's thank our speaker. So do we have any questions for Eric?
I think I have a question. So Eric, so in a few slides you mentioned about your the electron polarized E plus and E minus beam, you can have sensitivity on the higher twist. And you mentioned, I think it's page 19 or somewhere, that you said if the ALU or some term can be 0 if there's no higher twist effect. What exactly it means to have 0 higher twist effect?
If you, well, let's say that I see it like the development of like a development of an amplitude. If you don't have higher contribution, so everything what we, experimentally speaking, let's say, what we are when we do the interpretation of experimental data, we always assume leading order, leading twist and leading order. And this is all the formulas you saw was leading twist and leading order. So if you have higher twist contribution, this is going to be, these formula are no longer valid. You do have further contribution going into your cross-section, and you should see an effect of that. You should see that. So then I am always very confused with higher twist. I mean, to have a very nice picture of higher twist effect, but for me, the way I see it is, yes, further development in 1/q², And it's not development in alpha, but further development in T over Q square in the expression of your cross section.
I mean, so it's always there, right? It's as you said, it's 1 over Q squared, so you can never. Right? So you're suggesting that you can do a Q square dependent measurement to extrapolate the higher twist effect?
Yeah. Yes. Yeah. Well, you will have also leading order next to leading order, which okay, but at the lever arm, let's say that the lever arm in Q square that we can access at JLab, well, that's not ERA. We don't have that huge lever arm in Q square to do all these next to next and so on perturbation theory.
Okay, thank you.
Looks like John has a question.
Well, I was just going to say, I'm not sure about exactly what reaction you were asking about there, but I think the idea isn't that you expect you might have no higher twist. It's just that if you have a channel where there's no contribution without higher twist, then you automatically get to isolate those pieces without having to do the usual thing of separating a Q squared dependent piece from some other piece.
Yeah. In that sense, measuring something which is a deviation with respect to zero would give you a hint that there is something else. But higher twists are also appearing in the other observables. It is just that this one is zero in principle at leading twist. So if you measure something different from zero, you find something.
I see. Thank you.
So I have a question. Perhaps there's not a clear answer to this, I guess. So you showed a lot of really exciting measurements using this positron beam, and then you talked about the development of the beam. Is there kind of like a guesstimated timeline for when this may happen?
Yes, there is. Well, when this may happen, let's say that there is a plan, and I would not say if it is a guesstimated timeline, but there is a plan at least. There is a plan, and the Jefferson Lab management is working in direction of that plan, and the idea would be to start to see positron beam for this physics, for this high energy physics, to have that in 32, 33.
Okay, cool. So about 10-ish years.
10-ish years, and sooner, positron beam sooner at love. That's also something that we are expecting, and this is a place where we would like to try to develop an experimental program there.
Okay, also. Cool. Yeah, I'd heard that it was moving along well. I just didn't quite know what timelines we were looking at.
Yeah, 10-ish is a good, I would say, a good guesstimation.
Yeah. And then one other question on that is not timeline, but with all of these measurements, were really focused on JLab, Hall, ABC. So does positron affect the Hall D program at all? I mean, I know that they're a photon beam typically produced from the electron beam. So presumably lower intensity may just lower their flux, but is there anything going on there?
So at the time the positron beam would be available, there is no plan. Well, at this moment, everything can evolve, of course, but at this moment, there is no plan for a photon beam program in Hall D at that time. But if we could use the positron beam the same way that you are using the electron beam in order to do your photon beam, there is only a magnet that you need to change the orientation. This is the only impact if you want to use all D with photon beam and with initial electron positron beam.
Okay, yeah, that makes sense.
I also have a very technical question on LERF. So because it's a free electron laser, does that mean the beam structure is so the beam will be more pulsed instead of a continuous beam?
In fact, well, it was a free electron laser. There's nothing else now. Nothing is. It has been. Everything has been dismantled.
Okay.
So, but this will be CW beam, because that's going to be the one that you are going to provide to CEBAF. So you want to have CW there.
I see. Thank you.
Does using the low energy beam at LERF, does that impact the availability of the high energy electron beam in CEBAF? Like if there was like a low energy experiment going on, could CEBAF still work?
The only conflict I can see is on the cryogenic power, the global cryogenic power of the thing. This is the only place I see a conflict, a possible conflict, but this is really the only, and I cannot, at the moment, we don't exactly know how much cryo modules and so on will be there. So that's difficult to tell, but if there is a potential conflict, this is in that direction we should look.
Okay, yeah. I didn't know if like that impacted just like the injector or whatnot, but yeah, okay. Do we have any more questions for Eric? Okay, in that case, thank you for coming, Eric. This has been a really, really great seminar. Learned a lot about what's going on with the positrons. And let's thank our speaker again.